This class is. And you like everybody's not bothered, extra you're done with filling bracket. And people, you have the craft paper, and then people usually got it, and people implement that stuff like that. And other people build on the craft like a good work.
Realize I had layered deep.
Exactly.
What's the
Craft, everybody's coming in and reading.
It's literally just yeah.
Okay, you don't need
I
it.
got 13. That's a good question. It's more than the same.
Yeah, because they just have a good little
Okay, let's get started again. So it's been a week. Sorry about canceling lecture on Tuesday. I didn't get you to watch anything, so we'll just go from where we left off. Okay, so we were turning through DRAM. We're taking a journey through the GPU architecture. We at least have some basic understanding of how the core works and different types of research people have done in the core. And now we're trying to understand the memory system. Okay. And we started off last lecture by going through, or ended last lecture, talking about how the memory system isn't just memory, right? It's not just this like blanket thing where you just send it an address and it gives you back the data. It's actually a highly parallel, highly distributed system spread across. And there's this picture of, the inverted triangle for what a memory system looks like, starting with the very top level, which is a channel, which is controlled by a memory controller, which is a specific piece of hardware that knows how to talk over the pins to a DRAM. Then it breaks down into DIMMs, and then ranks, and then chips, and then banks, and then the rows and columns, which you probably know about, right? Every memory is actually a square, even though to the programmer it's this big linear array. It's the actual physical storage itself is implemented as a rectangle, because you can't physically lay out, whole, 4 gigabytes in one sort of linear thing, right? It has to be compartmentalized. And there's this row buffer hit effect, which we sort of talked about at some length last lecture. And then we talked a bit about, where did we end? I think we ended somewhere here, because there's a lot of repeated data in these slides. We sort of went through the fact that, so here's your DIMM, right? And the DIMM in this example has 2 ranks. And a rank is sort of like a big logical chip. Okay, it's like if you bolted all the chips together and you got one giant chip, they all operate together, because we can't actually build a chip that's big enough to service, for example, an entire cache line, right? We can't feed out 64 bytes from this thing for even a CPU cache line. So we feed out, 8 bytes per chip among 8 chips, and then you get 64 bytes, okay? And we'll see how that works in a second. To look at this logically in terms of like just concretely telling you what a memory channel is. So a memory channel, these are the pins, right? These are the pins that actually come out of the memory controller. They're running across your PCB. They're going to the memories, the memory chips themselves. And, we have some pins associated with the address and command. So what is the row I want to light up? Do I want to initiate a row read? Do I want to initiate a column read? What is the address of the column? All of that is in some control bits. And this is temporally shared. So unlike an SRAM where you can sort of like read the row and column all in one cycle, for DRAM, you'd open up a row and that would be one address, and then you'd send the column address. So DRAMs have these things associated with them called RAS and CAS, column address strobe, row address strobe. You've probably heard of these. That's because you have to sort of strobe it or send it the row, and then it takes some time for that to become active, and then you have to strobe it and send it the column. And each of these have sort of timing characteristics, in terms of nanoseconds. And then, of course, we've got the actual business of the bus. So this is the data that's coming back from your chip. In this particular example, we're showing 64 bits of data, but that could be, fungible based on whatever the configuration of your memory system is. And as I mentioned before, a rank is like one big logical chip, because we can't actually output, for example, 64 bits from one chip alone. So we would output 8 bits from 8 chips in this example, and then be able to wire that up to the 64-bit data bus that's running between your memory controller and your memory system. Okay, questions on this? Do ranks make sense? Okay. And then inside of a chip, there's actually multiple banks because it takes some time to read things out from each individual bank. And we want to have a bunch of storage inside each chip. And we can't just make it bigger, right? If we want more storage inside the chip, we can't just make these rectangles larger. So we add more rectangles, and that increases the capacity. And it also gives us an ability to overlap the accesses. So you can initiate, a row address strobe to one bank. And then while that's processing, you can initiate another row address strobe to another bank, for example, and sort of start them off and start overlapping their reads or their writes, so that way you don't waste time. Okay. And then inside each individual bank, of course, there's these things called row buffers. And when we read stuff out, we get much more data than maybe we wanted. And in this example, we're showing 1 byte, yes, per column that should read out, and then you sort of switch to select which of those 1 bytes you want in the column mux. Okay, and the row buffer, like I said before, this could just be implemented as there are sense amps in all of these. So sense amps are these analog circuits that try to detect very small changes in the voltage or current levels, so you can tell whether the bit is 1 or 0 very quickly. The row buffer could just be simply the pins that come out of those sense amps, and that's just held constant, or it could be latches where you latch in the result after it's sort of been read out. And that's an implementation dependent thing. It doesn't really matter. What matters is that when you read out that whole row, you can get quick access to everything on that row, as opposed to trying to access something on a different row. Okay, so let's talk about mapping the physical address space to the memory system. So now this is not the virtual address space. So this is after TLB translation, after page table lookup. This is the bits that you have for the physical address. I have to take that and then somehow map it to this massively distributed and parallel system. And in a simple example, I'm going to use a CPU example, okay? And I'm going to assume you have some Core i7, and I'm assuming that the last level cache has a 64-byte cache block, which means that every access that comes from the memory controller is going to want to fill 64-byte block. So that's the atom at which I'm going to go to this memory system. In this example, I have a dual channel system, okay, and I'm going to access. So if I'm going to put 1 cache block on 1 channel, and then I'm going to have 2 ranks on that channel. So this is rank 0, and this would be rank 1, which would logically be the other side of that chip, or the other side of that DIMM. And I need to somehow take addresses 0x0 through 0x40, which represent the first cache block, and then spray that into this memory system somehow. Okay. So there are different ways I could do this. Here's one example. So if I had 64 bits of data, so this is 64 bits, and I had chips that each could output 8 bits of data. So I'm essentially getting 1 byte from each of these. And so then at the end of this, I will have how many bytes on this data bus? 8. This is going to be 8. This is an 8-byte data bus. Okay. I know the numbers kind of line up, but it's not a whole cache block. Okay. So when I go to read out my cache block, if the width of my memory channel is 8 bytes, what does that mean? You need to have 8 cycles to fill your cache block. Okay, so your memory system is operating at some frequency. There's clock domains everywhere in modern circuits. Your core operates probably around 1 to 4 gigahertz. Memory systems tend to be slower depending on the memory technology, somewhere in the range of megahertz to low gigahertz range. And what that's talking about is the speed at which you can clock out data on this bus. Now, the bus won't necessarily be wide enough for the atom that you want, so it will maybe take multiple cycles to read out the data. So in this particular example, I've got my 8-byte cache block. I can only get 1 byte from each of these chips. This is contained in 1 rank. And so in my first cycle, I'll actually be lighting up, in this case, 8 chips. So the cache block is actually distributed across these 8 chips, okay? Because they're all in the same rank. Okay, I'm accessing with the same address. I'm telling them all to go to the same row, telling them all to go to the same column, but they store logically different data. They have logically different parts of the cache line inside of them. But that only gives me 8 bytes. Okay, so that gives me the first 8 bytes of my cache block is coming from each of these chips. Now, if I laid this out in the same way, where do you think the next 8 bytes of my cache block should live? in the next what?
The next column, right?
Next bank. Next column. Next bank is rough, right? I know I want this right now. So I already lit up the row. Okay, I lit up the row of this bank in this chip. So if I've got the first 8 bytes of that row, it's really easy for me to get the next 8 bytes of the row. So I don't want to go to a different bank to do that. I'm going to keep myself in the same bank and be on the same row to maximize locality. So a sane way to lay this out would be to put the next 8 bytes, again, distributed across all of these chips inside the next column in that same row. So now, so my memory controller has this job, right? This is what the logic inside the memory controller does. Like basically the L2 or L3 cache says, I need 64 bytes from this address. Then the memory controller says, all right, I know that my width is 8 bytes, so I need to break this down into 8 individual accesses to this particular rank, to this particular row, to this particular column, and it starts sending out those requests and then curating the data as it comes back. Okay, that is the memory controller's job. And in the same mapping, like I said, we'd light up that row for the cache line. So we're actually lighting up 8 different rows in 8 different chips in 8 different banks, right? But logically the same bank in each chip because this is a big rank. And so then the next 8 bytes would come from the next section and so on. And so if your row was long enough, which they tend to be, then for one cache line, you would have 8 accesses. The first one would take the longest because you'd have to open up the row, and then the subsequent 7 accesses would all be row buffer hits and be able to service them relatively quickly. Okay, if you always knew you wanted a 64-byte quantum from the memory system. Okay, questions on this? Yep.
So when you put it back into the cache, it's put in these chunks of 8 bits.
So there'll be a buffer. So your cache, so a cache is only managing things at the granularity of a line. Right. So, I mean, you could orchestrate it however you like. You could keep the valid bit invalid and sort of store it in the cache as it comes back. But now the cache needs some way to account how much of it it's filled. What typically happens is the memory controller is going to buffer this thing and then reply to the cache once it's got the full 64 bytes.
Okay.
Okay. Because when you put it in the cache and you set the valid bit to 1 and you put the tag in there, that means it's good. That means that whole line is good. So you need to have all the data. Okay. So there's going to be some buffering mechanisms in here to sort of keep this stuff around. And yes, you could implement it in the cache, but now you're sort of punting some of the complexity of that buffering down to the cache, and then it makes it harder to hook it up to another memory system. So usually this just happens in the memory controller. Okay, other questions? Yep. Yep.
This is still taking 8 clock cycles, right?
So this is still taking 8 memory system clock cycles.
But what if, in addition to accessing the next column, we also access different banks at the same time?
So that's not really possible because the address pins, right? You're also pin limited on the address.
Yeah.
Like every time I go to another column, I'm not showing it here, but there's the address pins. I need to send a CAS, and that CAS has a location, and I can't also send the row command unless I widen my data bus. So in typical DRAM memory systems, if you're going to read from one row, you have to do RAS, CAS, 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 CAS. If you wanted to light up different rows in different banks, you'd have to send separate commands, right? And then that would take extra cycles, But what would usually happen is that this first RAS takes some time. The first, like, opening up that row takes some time. So if I know I've got other cache blocks I want, I can do a RAS to another bank in that time, right? And who keeps track of all this? Like, what's in flight? The memory controller. Like, it knows what it's asked for. It knows how long it's supposed to wait for each thing. And then it just makes sure that it adheres to those rules. Okay, yeah.
Since the limit is like the data bus.
Yep.
Is there a way to expand it and use the other channel as well to spread the data across the whole?
Yeah, so that's a good question. This is all in one channel. So I'm assuming that the cache block is in a single memory channel. It doesn't have to be. We can play with the bits in the physical address however we like to spray the data in whatever crazy way we want across the memory system. So if you wanted to instrument channel level parallelism for one cache block, you could. But now you would have half the cache block stored in these banks and half the cache block stored in the other banks, which is okay. it really only matters if you don't have enough parallelism to initiate another cache block access, which usually isn't true with prefetchers and multi-threaded systems. And even an out of order processor is going to have like 7-8 loads byte or more from each individual thread. So you usually have enough blocks in demand that you can soak up the channels without having to spray each cache line across. But that's a good question. Other questions? Yeah.
When you end up loading a row, does it actually load all of the banks of the same chip for that given row? And then it just switches between each of those banks?
No, so it's initiated on a particular bank. Sense amps, so let me think about this. So every bank will have its own sense amps associated with it. Okay. And again, you can design this differently, but typically if you want to initiate parallel column at row address strobes, you need it to like start sensing the output as quickly as possible. So each of these individual banks that are stacked on top of each other in this diagram would have their own row buffer. And then you would be logically switching between those row buffers when you went to go access different banks. Does that make sense? Yeah.
That's because of the limitation on the pin.
And that's pin limit, right? So the internal parallelism of the memory chip is much larger, right? That's why sometimes PIM works. PIM is this thing called processing in memory, right? If you do digital processing in memory, like the amount of throughput you have inside the memory chip is actually far greater than you have outside of it because you're pin limited. This is all inside the package, all of these banks that are, this is all inside one physical package. So I've got a lot more parallelism in here than I do once I go outside the package where I end up being pin limited. Good question. Other questions? Yeah.
So you said that to get like multiple columns in one row, you need to set multiple like gas.
Yeah.
commands.
Well, yes, correct.
Like are those pipeline or like how does that work?
Well, what do you mean by pipeline? So the assertion is that, right, so does it take one cycle to do a cast in effect?
Right.
Yes. So you can pipeline those. You don't have to, like if there's internal pipelining, this is a simplistic diagram where it's sort of assuming that as soon as you do the cast in that same cycle, the bit's going to come out on the pins. That may not be true. It may be a cycle later, which means pipeline. Again, that's dependent on the design of the memory chip, but it's possible. Other questions? Okay. All right. So to get this 64-byte cache block, it's actually going to take me 8 IO. And we say IO, this isn't actually like, disk IO. This is memory system IO. Cycles to transfer. And again, what rate is this? Well, it really depends on the memory. Like when you go and you buy your DDR memory from Best Buy or whatever, there'll be megahertz on there. It'll be like 200 megahertz, 500 megahertz, whatever. That's what this frequency is the frequency at which it can push that data back out to the pins that connect it to the memory controller. Oh, I have a question on chat. Let me see. I actually saw it. So shouldn't it take 4 cycles considering we read data on both the rising and falling edge? We're not gonna, okay, so if it's dual data, so when I say good point, so it's the effective rate. So the clock, right, your clock goes up and down. You could choose to read either just on the rising edge or just on the falling edge or on both. If you read on both, then you basically are doubling the frequency. So yes, the data rate, if you're doing dual data rate and reading on both sides of the clock, is going to be double whatever the clock frequency is. I'm sort of abstracting that away and assuming that like this is as fast as you can read stuff out. And the upside of doing that is obviously you save energy because you don't have to like cycle the whole clock to get the thing, to get the next, right? It's a trade-off between do I make this clock faster or do I just read it on both edges, right? And if you make it faster, then there's more transitions, so it costs you more power. If you just read it on both edges with a clock that's half the speed, then you're wasting less power in clock transitions, right? So I'm abstracting that away, but yes, you're right. If you're reading on both edges, then it's actually going to be, it's going to take you, 4 clock cycles to do this. Okay. Good question. All right. So what is the latency here? So let's break down the amount of time. So everyone knows that, yeah, it's slow to go to memory, right? Like the sort of standard, what is the ballpark, how many CPU cycles it takes when you miss your last level cache? Any guess? What if somebody asked you this on your 565 exam, what would you say ballpark? How many cycles? 100 cycles, 300 cycles, somewhere around there. depends on the relative ratios of the memories. If you're running at a 4.5 gigahertz CPU, then maybe it's going to be a few hundred cycles. If you have a memory system fault or something, or even if you have to walk the page table, it's going to be even longer, right? If it's best case scenario and maybe the row is open, then maybe it's like 100 cycles, 90 cycles, that kind of thing. Okay. But where does all that time go? Okay. So I go from my CPU, and let's say I don't have a caching system, and like I'm just going out and I want to go give me this address. Where is the latency coming from? The first component is what we call the controller latency, because there's queues in this thing, right? You don't go directly to the pins of the memory. We have to have a memory controller. So the first place it goes when it goes to the memory system is to some queues inside the memory controller, and then there's going to be some scheduling that happens. So there's going to be some delay in just even getting to the head of the queue and getting your turn at the memory system. Okay, so that's the very first component of delay once it hits the memory controller. Then it's got to break down that access, because a load instruction just says address. Okay, it says go read address and for this many bytes or whatever, right? And then then the memory controller has to take that and essentially split it into a bunch of DRAM commands. It has to split it into, potentially pre-charging, potentially RAS, potentially CAS, based on what it knows is going on inside the system. Okay, so after you've done that, then maybe you have your set of commands here that tell the memory what it needs to do, and then there takes some time for the controller to actually send that out to the memory system. Right, this is a real system with pins. It takes time to transfer that then to the DRAM. And then we have to go take a look at what's going on inside the DRAM. So what is the latency of the individual DRAM bank once we sort of know where it is and we're sending it the right commands? So if the row is already open, then all we have to pay is the CAS latency, right? So this is part of the reason why it's not just the caching system that makes memory accesses variable. It's also the memory system. If the row's open, it's quicker. If the row's closed, it's not. So if it was already open, then all you have to pay at the bank level is just the CAS to read that little chunk that you want. If the thing is already pre-charged, okay, then you have to pay the RAS and the CAS. So you have to open the row, and then you have to column address strobe, and then if it's not pre-charged, then you also have to pre-charge the thing, then do the RAS, then do the CAS, okay, which is sort of the worst case at the bank itself. Then after you finally read this out, then there's additional time to go from the DRAM back down to the CPU. So there's some buffering that happens inside the memory controller, and then eventually the memory controller has to spit that back down to the CPU. All of these things are connected through some type of interconnect. This DRAM to CPU transfer time after the data is in the memory controller is usually pretty fast because this is some on-chip interconnect. There used to be that the memory controllers were not on chip, right? Like early Intel chips, you'd have a separate chip on the PCB that was the memory controller, right? It was like different bridges, right? You maybe heard of North Bridge, South Bridge, these kind of designs. Like it was a big deal. Like Moore's law is great, right? We get lots of transistors. We can pack the whole memory controller onto the chip itself. So this latency has gotten a lot better than it used to be back when the memory controllers were on the board. And the same is true in GPUs, right? The memory controllers are on chip. That's what those memory partitions are. The only thing that it wires out to is the individual DRAM chips themselves. Questions on this? So this is sort of the lifetime of what happens to your access once it goes to the memory controller. Yeah.
Why can't we pre-charge all the rows?
You could, but this is expensive, right? So it depends on what strategy the memory controller is using for pre-charge. Okay. So the worst case is that it's not pre-charged, and then you have to go do it. Other questions? All right. All right, so we have multiple banks. And again, this is for concurrency. So we've seen the banks, but we haven't really talked about how we use that concurrency yet. So you have banks that enable concurrency, and then you also have multiple channels that can enable concurrency. Channels are better in some ways than banks because they're whole new sets of wires, right? But they're also more expensive. So you get only so many channels based on how much you're willing to pay from a pinout of your chip. Actually have separate data buses. And this will increase the total aggregate bus bandwidth. This is how GPUs get their high memory bandwidth. There's just a whole lot of wires coming out of the GPU chip on the PCB that connect to many parallel memory chips. Okay, so I think I don't know what the Blackwell count is, but in recent generations we've had on the order of 10 to 20 sometimes 30 memory controllers on each chip. In the CPU, it's usually like 1 to 4. Okay, so you get all of these extra pins to drive increased bandwidth in the memory system. Okay. Right. So enabling more concurrency requires reducing bank conflicts. So we have the same problems here that we had for shared memory, right, in GPUs. We have to spray our address space across all this stuff. And in the ideal case, it's sort of perfectly distributed. So every access is going to, we're able to light up the entire system all at once, right? And that peak memory bandwidth number, that sticker on the back of the box in the GPU you buy, assumes that you're always lighting up every cycle, every memory controller. But that's not true. You'll have bank conflicts within the memory controllers, meaning you need to go to the same bank twice for 2 different things. You'll have channel conflicts. Those are actually disastrous because now you're not even using the pins. So if you can't cover a channel conflict, meaning that 2 cache lines, for example, want to go to the same memory channel in a 32 memory channel system, then you're basically wasting all of those other pins. It's a huge disaster. And if you did something similar or simple like a linear mapping, right, then weird things like accessing the first word of every page will just be a complete disaster for you in your GPU memory system. Because if you lay the first cache line of the page across one memory controller and the next cache line of the page against the next and the next and the next in this linear fashion, unless you have a workload that is playing nicely and streaming through this perfectly, if you just if all the threads are accessing the first byte of the first page, or the first byte of their page that they're going to work on, they're all going to bang on the same memory controller. And now your memory bandwidth is going to be a factor of 32 less than what the sticker is, because you're not lighting up all the other 31 channels of the memory system. Okay, so conflicts in this system are disastrous, and we try to make sure we try to mitigate that as much as possible. And then the question is, well, how do I do that, right? Like, how do I actually figure out how to map this thing? I could have some complex algorithm, right? Like operating systems sort of have this luxury where they have milliseconds to make decisions, so they can have some sort of software that runs some kind of algorithm, looks at the distribution of the data that's going through it right now, and then decides where to place things and maybe moves things around. We do not have that luxury in physical memory mapping, right? This needs to come back as quickly as humanly possible. And I cannot, every time I change the mapping dynamically, I have to move data, which is probably not worth it, right? Because maybe I got some better result from changing the mapping, but I had to move words or pages in and out of DRAM, and that's expensive. And we really don't want to do that to programmers. So we usually do this by essentially just looking at the physical address, the same way that we look at the address when we're doing cache mappings, right? You remember when we looked at well, what set is this in the cache? Or, what is the tag? We just looked at the address and broke down the bits, right? Basic 565 stuff, even 437. Lower amounts of bits are going to be associated with, the block offset, and then you've got a few more bits that determine, your set index, and then the upper bits are going to be the tag. We're going to do a similar thing here, except instead of mapping it to sets, we're going to map it to all of these different components, right? We have to map it to channel, to bank, to row, to column. So we're going to have some bits in the physical memory address. Again, this is the physical address that sort of tell us which of the components this thing is going to live in. And this greatly simplifies the memory controller's job. Because remember, I told you it's the memory controller's job to just take this address, tell you where it is. If it's some dynamic mapping, that's expensive. So I'm just going to take a static mapping and then do that. Okay. And generally in memory accesses, you should sort of have an intuition about this. Lower bits have more entropy, meaning that they change more frequently. Just think about the way you write code. You don't usually jump between gigabyte chunks of data, but you often jump between bytes or kilobytes of data. So the lower bits move around more. And the upper bits are much more constant if you just look at the stream of accesses in any given program. And then we're going to add some hashing functions, okay? Just to get rid of this pathological cases, we're going to do some XORing, right? So you should have read papers in 565 about doing this for trying to avoid conflict misses, right? In cache systems. It's a similar principle here. Instead of having conflict misses, I'm trying to avoid all of these collisions and bank conflicts or address conflicts in the memory system. And we'll get to that mapping in a second. So first, let's talk about how we actually use the variable, concurrent things in the system to cover latency. It's similar to what GPUs do to cover latency. We try to do many things at once. So if, for example, we did something where we weren't overlapping, so let's say that we're only going to access one bank at a time, right? So first we send the address. So our bus is limited. We can only send one address at a time. So we send the address of the row we want on the bank. And then we have to wait for that to sort of finish. And then we finally spit out the data. Then we send the next address for the next bank and what have you. If we were to exploit this bank level parallelism, we can queue up a whole bunch of different addresses. And again, the memory controller is doing this. It needs some buffer of all the addresses it needs, and then it goes and tries to light them all up. So that way I can exploit that bank level parallelism that's inside each chip and have each of these things running at the same time. So that way when they start spitting out data, my data bus is nice and busy, right? The whole game of a memory system is to keep this as busy as possible, as much as possible. The more idle this is, the more you're wasting memory bandwidth. These are the precious resources in the system, the data bus pins that connect the memory. Questions on this? Okay. Advantages here. So multiple channels. This is another way to increase the bandwidth. So you obviously increase the bandwidth, but the downside is that this is costly because this is a whole new memory controller, more board pins, etc. But it helps. So questions on memory channels. You guys should know memory channels at this point, or at least be able to distinguish them. Let's do some address mapping. Let's start out with a relatively simple system. So let's start out with a single channel system, and then let's assume that we have an 8-byte memory bus. So every time I go to memory, the data bus is going to give me back 8 bytes, just like our previous example. Let's say that the total aggregate capacity of the memory system is 2 gigabytes. I have 8 banks, and then I have 16,000 rows and 2 columns per bank. Okay. So this is giving you essentially the dimensions, right? So this is these are the individual banks, right? And what I'm saying here is that there's 16,000 rows, and then each row has 2,000 columns. And then I've got 8 banks in each of the chips. That's what I'm telling you here. Now, the memory controller needs to know this, right? So when you boot up your machine after you've installed a new DIMM, it needs to have a view of the memory system and know what it's dealing with, because it needs to map the whole physical address space to all of the memory, the physical memory you actually have in the system. Okay, so now I know what my memory system looks like, and I know how big the bus is for it. And so the first thing I can do is figure out how many total bits I need in my physical address space. How many total bits do I need in my physical address space based on this setup? 31. How do you get 31?
I added 1 gigabyte.
Okay, that's one way. Yes, what's another way? If I didn't show you this picture, if I didn't show you this, how could you know that you need 31 bits?
1 gigabyte is 30 bits.
Yeah, 1 gigabyte's 30 bits is a 2 gigabyte memory system.
Oh.
Okay. So the number of bits in the physical memory system is directly tied to the number of bytes that you actually have in your memory system, right? This is physical now. This is these are the things you actually can read and write to in the physical memory system. So I know that the total number of bits here needs to be 31. Okay, so now I can start with the bottom, and I can say, I'm going to assume that and again, you could do whatever crazy thing you want here, but this is just one sane way to do this. I'm going to assume that the lower 3 bits are going to be associated with the bytes in the bus. So when I do a transfer across, so I read out, I know I've got 8 bytes every time I do a read, those are going to be contiguous. Okay, so that's sort of the same way we laid out the cache block. Remember when we had that cache block where it's we read the lower 8 bytes and the next 8 bytes and the next 8 bytes. So these 3 bits will tell you which of those 8 bytes you're in, okay, on an individual transfer across the bus. Then I'm going to go and I'm going to put the next bits associated with the column. So these are the next fastest changing bits. So what this means is that the first 8 bytes are going to be here on a row. Okay, this is column, logical column 0 if I'm indexing it by 8. Okay, then where are the next 8 bytes going to be if I put the next 11 bits as the column bits? Different row, where? Different column, right? So I'm going to use this as my column index, these 11 bits. So the very first address, this is 0. Okay, and then, I've got the next 3 bits are just associated with the data that's inside here. Then the next address here is 1. So as I sort of like scale up this number, this goes from 0 to 1, which means that becomes the index for the column, right? So that means that in consecutive columns of a row, I am storing consecutive 8-byte segments of a cache line. Got it? No? Yes? Sort of? Some people have it, some people don't. If this isn't quite clear, you do need to sit with this and make sure you understand it. Okay. So now I put 11 bits here. Why did I pull this out of my butt? Like, where did 11 come from? Yeah.
2000.
Because I know there's 2000. I know there's 2000 columns. So that means that I know I'm going to have 2000 chunks of 8 bytes at a time. Okay. So that's 11 bits of the address space. So this will take me across an entire column. Okay. So my address space 0 through whatever the end of the row is all going to be contiguous across one row with this particular mapping. Okay. Now I go here, and the next 3 bits are associated with bank. So what will that mean? Where, if I've got like, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and then I go to 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Where is, and let's assume that it starts off with all zeros, and then it's all zeros and then 1. What bank does this address live in? 0. What bank does this address live in? 1, right? So that means that after I exhaust that whole column, the address space then switches to the next bank. Now, if I assume that the uppermost bits are the same, it's the same row on the next bank, right? It's row 0 if I assume that everything is 0, because then I take the leftover bits and I associate it with the row. So what I'm doing here is first striding my chunks of 8 bytes across each row. And then once I've finished with the row, I stride it across the next bank. And then when I finish with every row 0 in all 8 banks that I have on this chip, then I go to my next row. And then I do the same thing. And that represents how the addresses will be sprayed. And the memory controller just basically keeps this mapping in its mind. And then as you're shoving physical addresses at it, it's just cutting up those physical addresses and deciding which thing to light up based on what the physical address says. Okay. So this is what's known as row interleaving. Okay, so I put the sort of lower bits are sort of a no-brainer, right? Those are the bits and the bytes in the bus. And then the very first thing I do is then try and like spray the thing across the columns and then wait and then spray it across the banks. Now, this one is weirder. So this is what's known as cache block interleaving. And this will result in consecutive cache block addresses living in consecutive banks. Now, I have to know how big my cache block is here to do this. So I'm going to tell you that your cache block is 64 bytes, which is going to take how many bits? 6. Thank you. Good. 6 bits. Okay, so let's start at the bottom. Easy, right? So the bottom 3 bits are devoted to the bytes in the bus. Now I need 6 bits. And then what I want to do here is I want to put every consecutive block in a consecutive bank, which means that, cache block 0, bank 0, cache block 1 should go in bank 1. Okay, so now, but I don't quite have 6 bits in what's on the bus each time. So now I have to take my column bits that I put here and essentially split them. So you're going to split the column bits such that you get 6 bits total here before you start varying the banks. So that way every cache block is going to be in a different line, such that if you're accessing consecutive cache blocks like a prefetcher, right, you can light up bank 0 and then light up bank 1 and then light up bank 2, etc., to try to exploit that bank level parallelism if you have, this sort of repeated access or this striding access pattern in your cache blocks. But I need to figure out what to do with each individual part. So I'm actually going to have, I actually have to split that 11 bits associated with my column into 2 places. So 3 bits are for the low column, and then I take the rest of the remaining bits and put them in the high column bits. So it now becomes a little bit trickier to think about the way that the data is laid out in the banks themselves, right? Because the real issue here is that the block is not as wide as the row, right? So you're going to have, one whole cache block. So with this mapping, I've got this super wide row, and then I'm going to have one whole cache block live in bank 0's row 0. And then I'm going to have one whole cache block live in bank 1's row 0, right? And that's the mapping that you'll get. But logically now, my address space doesn't nicely just like fall across the row like it did in the first one. So your data is actually now sort of sprayed across different banks in that same chip from a logical address perspective. Does that make sense? And then once you sort of finish striding across all the banks that I have, I come back and I start striding columns again. So that means that after I've done like 0 through 7, I place them in each of the banks that I have, then I come back here and then I start placing the next one right here, right next to it, right? Because I'm sort of like skipping these bits, right? And so this is the next bit that I care about in the columns, which is just going to be the one right beside. And then I put, the 8th cache block in that same row. So essentially, if you pulled out one row of your DRAM, you're getting cache block 0, and then cache block 8, and then cache block 16, etc., because you're spraying the blocks across the banks. And all you have to do is this weird kind of address mapping, and you can achieve that level of parallelism. And this is a static thing that's sort of done when the memory system is trying to figure out how to do this. Does this make sense? Are there questions on this? I will expect you guys to understand this physical mapping. So if it's not clear right now, please do ask. Yeah.
More of a, just so like if you were going to spray the cache block across all of the banks, or you would just have the bank, rather than doing one cache block in each bank, and
Yep.
with the bank little bits.
Yep. So basically, since I know that these 6 bits are going to be consistent across a cache block, everything I shove down here is going to distribute the block across whatever thing I put down there, right? And again, this is arbitrary. I can be an absolute idiot, right? And I can put a bunch of bits of this down here in the lower bits and then just not use all 8 bits that I get from the memory system every time, right? You can do this however you like. This is just like kind of a sane way to do it. Other questions? Yeah.
So I'm having trouble visualizing it. Is that the same as the previous diagrams in the previous slides where it was the different banks of 0, 1, 2?
So the previous diagrams was this one, okay? Where I had like this diagram, where did I put it?
Yeah.
We have one with a block, yeah. So this thing is the first mapping I just showed you, where the cache block, well, actually, am I even telling you that? I haven't given you enough information in this slide to tell you that, because I haven't actually gone between cache blocks here.
Okay.
Right?
Yeah.
Yeah, makes sense. And I also didn't distinguish between a rank and a chip in this example. I'm assuming that the chip is a whole rank, right? You don't even really care how many chips you have. You just care about how wide your rank is. Okay. Other questions? Yeah.
Wait, so then with catalog interleaving then, so is it like the first half of the block is stored in
So in each of these examples, since the bank bits are so high up in the address space, the each cache block is contiguously stored in a row. Okay. Because I'm changing the column first, right, in both cases. So that means that I'm moving across the row for each cache block. Okay. So this one sort of maybe makes more sense to think about. This one is better for concurrency, especially if you've got something like a stride prefetcher that's asking for sequential cache blocks. Okay, other questions?
The byte in the bus, is that started across multiple different chips depending on like the 0th chip?
Yeah.
000 or?
Yeah. So I've abstracted away the concept of a chip versus rank here. I'm assuming that this is just one big wide rank, essentially, right? I'm assuming that your chip has this 8. This is like a big chip, the way that I've described it, where you can get 8 bytes out at a time. In reality, it would be one rank sprayed across 8 chips if each of them only had a small interface. Make sense? Like that is the magic of a rank, that I can have tiny chips, but bolt them together to make them look like a logically large chip. I haven't really even described rank here, right? I'm just saying, I'm assuming that it's a big chip because that is essentially logically from the physical mapping of the memory system what it is. It doesn't matter that it's actually on different chips. Does that make sense?
Yeah, just what actually happens is chip 0 would take
Yes.
000 off the bottom of it.
Correct,
Right.
correct. So the cache block itself, if your rank is composed of multiple chips, which in a real system it usually is, then that block is not all on the same chip. That block is sprayed across,
They're all accessed in parallel.
but they're all accessed in parallel, so it looks like the same thing. Yeah, but if you're trying to like, you know, we like physical things, right? We like to like touch each of the individual ICs and be like, all right, 8 bits of this cache line is here, and 8 bits of the cache line is there, and that's what's happening. Make sense? But physical address mapping doesn't care because it can't individually access the chips, it can only access the ranks. Good question. Other questions? But it's also weird to think about, right? Like your cache block is actually like parts of it are in each of these chips. Yeah. Other questions? Yeah.
Why was the kind of split up of the column bits kind of arbitrarily at 3 bits for the low column before you start spraying across the bank?
Because I wanted here to ensure that consecutive cache blocks lived in different banks. That was my stated purpose of this address mapping. So that means that I need to make sure that for like every 6 bits are going to be consistent across the cache block. We're in agreement of that, right? So that means that I need the bank bits to change as quickly as the cache block changes. So I have to put the bank bits right at the edge of 6. Make sense? That's why I did it. Now, I could have, stupid, but I could have like put the rows here instead of the, like I could stride the rows first instead of the columns, but this is dumb, right? Because now the fast changing bits are going to change rows and you're going to have to do RASes to light up the other rows. So rows always come last because those are the slowest changing bits. And that's the expensive thing. It's like every time I change a row, I've got to go light up. I have to pay a cost. So I keep the columns low and then stick the bank bits in where I need them. Yeah. Yes.
So then, yeah. So then, So one of the differences between a row and cache block would that mean that for row deleting, like for one cache block, you would have different parts of the block all stored across one row, whereas with cache block deleting, the block is stored across different rows. Yeah.
All right, I don't know. I heard the first part of your question. So are you asking about one of these specific mappings or a hypothetical mapping?
Oh, sorry. Yeah, these mappings.
Okay. For these mappings, the row changes last. Okay. So I'm going to put cache block 0 on row 0, and then cache block 8 is going to be on row 0, and then cache block 16 is going to be on row 0. And then as soon as I run out of rows, or sorry, a column. Yeah, as soon as I run out of columns, I'm going to move to the next row. And then I'm going to do the same thing. That's how this will look.
Okay.
Yeah.
Even with this bank level parallelism, you can of course do all the accesses at the same time of consecutive cache blocks. But for transferring to a CPU, GPU, anything else, you're pin limited still.
You're still pin limited.
So is the idea just like that there's going to be like some sort of almost like a burst transaction where you just assume increment, and every time you see a signal, you say, oh, I have the block immediately ready to go. I like just change the mux basically on the final output. Is that the idea of why it's faster?
It's faster because when I go, it takes some time for me to go to a particular row. Okay, that process of lighting up the row is much longer than just reading from a column. So I want to be able to initiate as many open rows as I can. And even, yeah, so, yeah, I don't know if I'm answering your question, but the cost really is like, if I don't do it this way, and I have a striding prefetcher, then, well, if I don't do it this way and I have a striding prefetcher, if I do the top one, it's maybe not that bad, right? Because I actually am still reading from the same row, right? So I still have a locality there. So as long as that internal bandwidth is able to keep up with the external bandwidth, it's okay, right? But it's not exploiting the bank level parallelism. So that means that I pay a higher initial cost because I have to wait, I have to RAS my first cache block. Okay. And so it's sort of like I end up getting 8 open rows instead of just having 1 open row. And in the aggregate, that allows me to cover the latencies better. Does that make sense? So I see what you're saying. I think that's what you mean, right? It's like, oh, we're on the same row anyway, so why do I care? Right. But now you actually have 8 open useful rows, and then you can use that to effectively fill the bandwidth of the bus. And again, stuff's getting reordered all over the place, right? Like, this is why memory consistency is hard, because it's like, the memory system just wants to reorder all of it to try and like keep things busy, but like the programmer doesn't know that this is happening. Yeah. Does that answer your question?
Yeah.
Good question. Yeah.
Would it make any sense to do an 8-byte cache block interleaving so that you have like a byte, bank, column, and then row?
So byte, bank, column, and row. So basically put your cache block across banks, right? So you have 8 bytes.
Would they have any advantage over row?
You're lighting up all the banks on every access. Again, it would depend, right? So you won't. So because you'd want them all at the same time, right? The nice thing about the prefetch is that you actually want them at different times, whereas the cache block, you would need it all at the same time. So lighting them all up, if they all take the same amount of time, if you RAS, and then it all comes back kind of the same time, and then you feed it out through the muxes, that'd be better than just like opening the row and reading 8 times. You still have to read 8 times either way, right? So it may not be an advantage to do it that way. The nice thing about the cache block is that it actually wants the first block first, and the second block second, the third block third. So you're able to overlap them, but it just depends on the relative bandwidths of the internal versus external bandwidth of the system. So I don't think there's a huge advantage, but they usually don't do that. They usually don't stride it across banks. Okay. Other questions? Yeah.
Do banks share their RAS with the cache, or is there also a bank select?
So every cycle you can only do 1. So there's a select. Basically, it's saying which bank I'm selecting this particular cycle. So I'm command limited in that way. Like I can't. Now maybe some memory. This would depend on the implementation of the memory technology. Like I think some of the higher bandwidth memory technologies allow for multiple bank RAS signals, but the typical flow in like standard DDR is 1 RAS at a time for 1 particular bank at a time. Good question. But yeah, you can be more aggressive, right? And again, it just depends on how you define your memory system interface. All of these minute details, this is what's in the JEDEC standard that defines what DDRX is and what GDDRX is and what HPM is. Okay. Other questions? Yep.
What is more expensive energy or latency wise, striding across a column or striding across a bank?
So energy wise, cross bank is worse right? Because I have to light up end banks. So you're paying the cost of all those sense amps being on when you could just, you're gonna turn on the whole row no matter what you do, right? Latency wise, what do you mean? So you're saying like,
Having those 3 bits at the lower column makes
Yeah.
more sense if it's more expensive to stride across banks.
having the 3 bits, so having the second mapping is,
Instead of putting the bank bits in place of
Yeah.
lower column will make more. Having the second one instead of bank and lower column exchange would make more sense if striding across banks is expensive in either in pure latency.
I see what you're saying, for his example of trying to stride the cache line across the bank. Yeah, I mean, it's poor for energy if you can actually get it from the single bank. But, you know, if you know the access pattern is going to need those other, because if you think about it, lighting up the first one, consecutive stuff, you're sort of depending on it being on one row, and you get 1 row worth of stuff ready. If I stride things across the banks, I get 8 rows worth of stuff ready, right? And that's the win, is that it's ready sooner so you can keep the pins active long, because there's 8 times as much data, but obviously that's costing you energy to keep all that state. Make sense? Okay, I'm gonna move on from this. We can also do tricky things. Okay, so it's not always advantageous to just take the bits themselves and do nothing to them, because then these strides can have these weird conflicts, right? We want to avoid conflicts as much as possible. So we can sort of randomize the way things are sprayed across to make conflicts less likely. So here's an example where I'm going to take, I think this is the bank index. So if I take my first mapping where I was laying things out, you know, across the row first, this is the exact same as on the previous page, and these 3 bits were traditionally what we use for the bank. I'm not going to just use those 3 bits. I'm going to take those 3 bits plus some bits up here in the upper part of the address, do some XORing with them, and then that'll give me my bank index. So now, you know, it doesn't cleanly go across in a strided way, but it's sort of swizzled around in a sufficiently random way that hopefully I avoid conflicts in a sort of the general access case. And you can make this kind of hashing or computation as arbitrarily complex as you would like. And it'll just perform better or worse depending on the characteristics of the access stream that you're seeing. And there's lots of work today that goes into trying to figure out in high bandwidth memory systems, especially on things like GPUs, what crazy math we should do with the bits of the address to try to spray it across everything, you know, on all of the, you know, different types of workloads that might get run. Now let's add the channel to the system. So that was a single channel system. If I want to add another memory channel to the system, then I need another bit. Okay, I need a C bit. And in this example, did I keep it the same size and then just double this? Yeah, so everything is the same size, but I now have another memory channel, which means I'm doubling the size of the memory system. So I have two 2 gigabyte channels. And again, the number of bits in this whole thing is just dependent on the size of your physical address space and how much stuff you actually have. And you could sort of spray the channel in different locations. If you put it up here, this is bad parallelism, right? Because this basically says that the first half of the memory space lives in one channel and the second half of the memory space lives in another channel. If you're running like a multi-process system and you know you've always got like 2 processes on the thing, and then your memory system, your virtual memory system is saying, I'm always putting the accesses for this application on this channel and all the accesses for this application on the other channel. You know, it's a good way to try to alleviate contention, right? If you're trying to not make it a security flaw. And it can work, but generally, if you've got one program and the channel bit's way up there, unless you've got a crazy program that's like jumping from one half of the address space to the other back and forth, this isn't really maximizing parallelism at all. So then you can sort of move the channel bit further and further down into more high entropy bits to try to maximize that channel level parallelism. And again, it operates in the same way that the banks worked. So you'll essentially be striding things across channels at the particular rate. So at this kind of funky configuration right here, what this says is my cache line is actually sprayed across multiple channels. right? So I've got like 8 bytes of my cache line on one channel and another 8 bytes of my cache line on another channel, which if all you're accessing is one cache line at a time ever, this is kind of what you want, right? Because you actually want to go to the 2 channels and light them both up to try to get the data. So the bandwidth for each block is going to be twice because you're going to get all those pins. But usually no modern memory system just has like one access in flight. So this is not usually profitable. So it usually ends up tending towards the higher bits for the memory channel. Right. And you should be able to look at, okay, so here is like a bunch of different weird ways to cut things up as I sort of move the channel bits down. And you should be able to think about, well, like where are consecutive cache blocks stored in each of these examples? Okay, so, you know, this one, the one cache block is like across multiple channels. In one cache, here we have one cache block in channel 0, and then the next cache block is going to be in the other channel. So the cache blocks are going to alternate between channels, which maybe isn't a bad thing if you've got a sequential access pattern. Here we've got cache blocks are going to be basically in parallel banks, right? And then eventually, once you exhaust all your banks, instead of just going to the rest of the column, you're going to go to another channel. And then you'll be accessing them out there. So the more parallelism, the more in-flight memory accesses you have, the better off you are moving the channel bit further up in the mapping stream. Fewer accesses, you kind of want the channel bit further down because you know you have less stuff to play with. Thankfully for GPUs, you know, we have lots of accesses, right? So we don't need to move the channel bit way down. It's usually further up in the address space because there's plenty of accesses to go around and you can light up the channels appropriately. Now, the OS can mess with this. If the OS is smart and the OS knows what the memory system looks like, the OS does do mappings. So if you recall your 565, there is a physical address and a virtual address. This is the memory system that you love and know before I taught you about what's going on under the hood. You know, a physical page offset, depending on, you know, how big your pages are. How big are the pages in this virtual memory system? 4K. If anyone ever asks you that, just guess 4K. It usually is. 12 bits, 4K memory system. So that means that all of these are going to be consistent between the virtual and the physical address. And then the thing the memory system gets to play with is this mapping, right? The page table is effectively a lookup table that takes physical page numbers and maps them, or sorry, virtual page numbers and maps them to physical page numbers. Now, if the memory system is smart and it knows how the memory controller, or if the OS is smart and it knows how the memory controller is like manipulating these bits, and it knows like, okay, I want these 2 pages to be accessed in parallel, it can try to do this mapping such that it like maximizes bank level parallelism, right? This is like next level OS optimization stuff where I know that these are going to be in different banks of my memory system just because of the mapping. So if I know that I've got good page level parallelism among these 2 pages, I'm going to try to put them in different banks, and it can influence the system in that way. Most memory systems don't worry about, like most OSs don't worry about this because now it becomes very tied to the actual physical memory mapping. So like a general purpose CPU OS doesn't really worry about this that much. The GPU does kind of worry about this. And it doesn't run like a full, you know, it doesn't have the same constraints as a normal OS. So, and it sort of knows what part it's running on, so it can try to do this physical to virtual mapping to try to maximize parallelism as much as it possibly could. And yeah, obviously there's like techniques that you can use, like page coloring, trying to maximize parallelism and avoid conflicts as much as possible, avoid inter-application interference, just try to, you know, avoid you feeling the fact that your machine is not actually your machine. There's multiple things running on it because, you know, this matters, right? Like if you talk about side channels, right? Everything in the memory system can be a side channel. If you're sharing the same banks, then how often you access it is going to affect how fast the other process in the system is able to access it. So once you sort of realize, and from a security perspective, once you realize that any contention in the system is a side channel, the whole system is broken, right? You can find, unless you isolate things, if you have to share things, then you're going to be able to create contention in some way. And the only question is how fast you can manipulate that contention to create side channel and like how fast you can transfer data across the side channel. There's no way to limit side channels or sort of covert channels if you're still sharing things at some fine granularity. Okay. So that's why security research will never end. Because nobody wants to fully isolate everything. And there's always going to be some way to like hack at whatever crazy thing you try to do to mitigate this. If you know what's going on, if they're fundamentally still sharing things and you can time things, then you can find a side channel somewhere. All right, anyway, that's my spiel on security. Okay, this is really, you guys should really know this, but let me just very quickly go through this. So let's talk about the cell itself. Okay, DRAM cell is different from an SRAM cell. How many transistors are in a traditional SRAM cell? 6. Thank you, VLSI people. I'm not going to ask you to raise your hand if you didn't know that. If you took computer science, maybe you don't know that. But everyone who does like any kind of EC or EE should know this. 6T SRAM cell, right? You've basically got 2 inverters and then some controlling transistors. That's not what a DRAM cell looks like. That's way too many transistors and way too expensive. DRAM cells are much smaller. Okay, they essentially have this thing called a trench capacitor. Okay, that's what this is. So this charge is not like the nice thing about the SRAM cell is that these inverters are like plowing electricity at each other. So they're holding the signal by themselves because of the construction of the circuit. That's not what we do in DRAM. In DRAM, we just charge up essentially a capacitor. And then whether the charge is on the capacitor or not determines whether there's a 0 or a 1. What that means is once I pull off that charge, it's gone. And I have to replace it. Okay. And it also means that I cannot perfectly ever isolate a node in a real digital circuit. Meaning that even if I don't access this thing, if I turn off this transistor and this thing is floating, there's no such thing as a fully floating node. And it's going to leak its charge over time, which means that even if I don't access the thing, the charge goes away. So there's a mechanism inside DRAMs to fix this. What's it called? Refresh. So if my DRAM is sitting there and it holds data I care about, I have to periodically go activate and pre-charge every row in every bank of every DRAM chip I have to make sure that that charge that was leaking away is restored. And I need to do it at a particular rate. And again, the rate I need to do it at is what's guaranteed by the contract in the JDEC that says when you build a DRAM, it better hold its damn charge for this long. Then the memory controllers are going to make sure that it's refreshed at that particular rate. And if you build a crap memory controller, then you lose your charge because the DRAM is going to forget it. Okay? Or if it misses its refresh or whatever. Yeah.
Has anyone looked into using the leakage current in the past to figure out what data is actually on the DRAM itself?
Not that I know of. This would be hard, right? Like, if you want to measure the leakage current, yeah, I mean, you can like physical access to. I mean, maybe there's a more clever way to do it, but not that I know of. Okay, to actually measure that leakage to try to figure out what data was in there. There should be some heat dissipation or something if you're leaking a 0, if you're leaking a 1 versus if it's a 0 that's in there that maybe you could take advantage of. Sounds hard though, especially over like, because if you just like pop a sensor on this thing, this represents, millions of bits across tens of banks. Like, how do I figure out? That sounds, maybe AI can do it. I don't know. Yeah.
That reminds me of a paper last year called Hot Pixels.
Okay.
Where they looked at temperature sensors in the GPU.
Yeah.
And they were able to reconstruct the entire screen.
Yes.
That's some real.
Yeah. So I know this paper. Yeah. So you can, but again, it takes a lot of tests, and so there are all these weird security attacks where you could like measure temperature and try and figure out what it's doing, and it's kind of crazy that you can do it. But honestly, if you have physical access to a machine, it's game over. I mean, the OS is not going to, if you're physically next to the thing, like the OS can't protect you, like you're done. Like the encryption of the data itself is the only thing that saves you, because otherwise everything can be lifted. Anyway, yes.
There's a huge security hole with the 64 milliseconds recharge as well, because if you know that it's gonna take exactly 64 milliseconds, then you can, hide something in there. And so the DRAM manufacturers like Micron actually have a classified amount of time, which is somewhere in the 40 or 30 milliseconds.
What difference does it make? So you're trying to, okay, so they don't tell you precisely how
Yes.
frequently they refresh.
Something like
Yeah, okay, yeah. So physically, it's about 64 milliseconds, but they may mess with it from an adversarial perspective.
because 64 is just the limit. You can go lower if you want to.
All right. Okay, I'm out of time. This is very simple. Okay, refresh. You can do it in two different ways. This is the only thing I wanted to learn from this. I can either just be like, I'm not going to refresh anything, and then be like, I'm going to refresh everything all at once. That's called burst refresh. Okay. This is nice because in this time when you're not doing anything, there's no interference. But then it sucks when you have to refresh every row in every bank. Or you can do distributed refresh where you're like, I'm just going to do this one, this one, and this one. And if you're smart, you can sort of like balance it out so you don't notice when the refresh happens. That's it. I'm going to let you go. Yeah, refresh sucks. It costs energy, but you really have to do it. Has everyone heard of refresh before? All right, fine. We're going to move on to GPU DRAM next class. I'll see you guys next week. Thank you.
Yes.